So now we're going to begin our discussion of carbohydrates. Friend or foe? I gotta say, I love carbohydrates, and we all need them. However, we can consume them in excess. So while we need carbohydrates for the extraction of glucose to provide energy and short-term storage molecules like glycogen, if we eat too many, we're going to store those as fat. And we'll see that later on. So carbohydrates are basically hydrates of carbon. They have a general formula of CH2O, with the N denoting the number of repeats or multiples of this general formula. For example, if this was a 2, the formula would be CH4O2. We can classify carbohydrates into 3 groups. Monosaccharides, which are the simplest sugars, cannot be broken down further. This is the smallest saccharide unit. Examples of these are glucose and fructose. Oligosaccharides, oligo meaning a few, usually range from 2 to 10 simple sugars that are connected by glycosidic bonds. And notice we use the term residues here just like we did with amino acids. So monosaccharide units are called residues. The simplest of the oligosaccharides are disaccharides. So these are 2 monosaccharides, again, that are linked by glycosidic bonds. Sucrose, maltose, and lactose are the most common of the disaccharides, and we'll be looking at those. Polysaccharides are polymers of simple sugars. They may be linear or branched and could have hundreds to thousands of monosaccharide units within that structure. So a little review of stereochemistry, and we'll do more of this when we actually start drawing these together shortly. Stereoisomers are going to have the same molecular formula. They'll be mirror images of each other, and we call those enantiomers. Mirror images are non-superimposable, and we'll discuss what that means when we draw these things together or take a look at some of the structures. Pairs of isomers that have opposite configurations at one or more of those chiral centers but are not mirror images are diastereomers. And finally, epimers are 2 sugars that have different configurations at only one of the chiral centers. When we draw the open chain structures of carbohydrates, we're going to use Fisher projections, and we'll use Haworth projections to draw the cyclic structures. And I want you to stick to those, please. So monosaccharides can also be classified as either aldoses or ketoses. Aldoses have an aldehyde head group. Remember, that's one of your organic chemistry functional groups. The aldehyde head group is going to be at the end of the carbon chain. Ketoses also contain a carbonyl group, but this is in the structure, and it's usually on carbon 2. So here's an example of a ketose. This is D-fructose and L-fructose. These are enantiomers, so they are mirror images of one another. So when comparing these structures, we have to keep in mind that we're only going to compare the orientation of the hydrogens and hydroxyl groups in this alkyl chain. And if we pretend there's a mirror here, we see that the reflection of this hydrogen gives me a hydrogen. The reflection of the hydroxyl gives me a hydroxyl, and the same here. So these are mirror images. We label them D and L based on the orientation of this hydroxyl group that comes right before the end of the chain. So this group is on the right, so it's a D configuration. This one is on the left, so it's an L configuration. So this is a flow chart or graph, if you will, of the aldoses. We're only showing the D conformations. In fact, in nature, the D conformations are what are utilized for energy and processes. The simplest or the smallest aldose is D-glyceraldehyde. This is an aldotriose. So this is another way we can classify carbohydrates, and that's by the number of carbons in the chain. So triose, 3 carbons, aldotetroses, 4 carbons, aldopentoses have 5, and finally aldohexoses have 6. So you'll notice that there are some carbohydrates highlighted in blue. These are the carbohydrates that you're going to be responsible for knowing the names and the structures. Now we're going to take a look at some of these in closer detail. As I've already said, D-glyceraldehyde is the smallest and the most common of the monosaccharides. If we compare, and the name isn't showing here, but this is D-erythrose and D-threose. So these are aldotetroses. They have 4 carbons in their chain. They are diastereomers. Okay. If we pretend, again, there's a mirror here, you'll notice this hydroxyl is a reflection, however, this one is not. So we would need an OH group here for that to be a stereoisomer. So these are diastereomers. This is D-ribose, D-arabinose, D-xylose, and Z-lysose. D-ribose is the most common aldopentose, and you are responsible for the structure of D-ribose, both in its open chain and its cyclic chain, or cyclic structure, which we'll get to when we discuss nucleic acids. And finally, the aldohexoses. Glucose, mannose, and galactose you are responsible for again. I want to point out that these are epimers of one another. So the yellow highlights here, well, wait a minute, where's the yellow? These are C2 epimers, sorry, glucose and mannose. So at C2, the hydroxyl groups are on opposite sides of the chain, otherwise they're the same. And galactose is a C4 epimer. So the hydroxyl group, where's C4? 1, 2, 3, 4. Hydroxyl group here is on, where did I lose my place there? The opposite side, if you compare the C4s in these two. So if you learn the structure of glucose, and you know mannose is a C2 epimer, galactose is a C4 epimer, you don't have to memorize those structures. So a little more terminology. Glucose, the aldose, and fructose, a ketose, can form ring structures. When they do this, we call the aldose a hemiacetal and the ketose a hemiketal. When these cyclic structures are formed, the carbon atom that's carrying the carbonyl functional group becomes an asymmetric carbon, or a chiral carbon, or an anomeric carbon is another term that we use. So these isomers of the monosaccharides are only going to differ by the configuration around that asymmetric carbon, and these are anomers. Okay. When we'll look at some structures of anomers as well. They are denoted as either alpha or beta, depending on the position of the hydroxyl group at that asymmetric carbon. Cyclic forms of glucose are pyranoses. Cyclic forms of fructoses are furanoses. So glucose would be glucopyranose. It's a 6-membered ring. Fructose in its cyclic form would be fructofuranose, which is a 5-membered ring. We are going to draw or learn to draw or convert, I should say, the linear Fisher projection into a cyclic structure, or the hemiacetal in this case. When this is a general representation of what happens during that cyclization of this molecule. A hydroxyl group in the alkyl chain is going to react with the carbonyl, in this case of the aldehyde, and form that hemiacetal. And you can see over here, this is a Fisher projection that it's showing that it's the C5 carbon hydroxyl group that reacts with the aldehyde head group. So we can get two forms when we turn this into a cyclic structure. We can have the hydroxyl group in the down position or in the up position. If that group is down, it is alpha. And these are D-glucoses. See that hydroxyl group is on the right. So we have alpha D-glucopyranose or beta D-glucopyranose. And these are Haworth projections. And this is the way I want you to represent these when you draw them for me. So this is the general reaction that occurs when we form a cyclic ketone. Again, there's a hydroxyl group within the chain that is going to react with the carbonyl group in the, of the ketone and form that hemiketal. In fructofuranose, this is the hydroxyl group on C5, but remember that our carbonyl group is on C2, so we have a reaction with hydroxyl on C5 with the carbonyl on C2. As a result, we get a 5-membered ring here. I forgot to point out the numbers of atoms in the ring for the glucose, but you can go back and do that yourself. We have 1, 2, 3, 4, 5. So we have a 5-membered ring. We have 2 carbons with hydroxyl groups outside that ring. Again, we have formed an anomeric carbon in which we can have that hydroxyl in the down position where it's alpha or the up position where it is beta. So this is alpha D fructofuranose and this is beta D fructofuranose. And this basically just summarizes what we've just discussed with respect to the cyclization and the formation of those asymmetric carbons that are called anomers. The hydroxyl group at the anomeric carbon is going to be on the same side of the Fisher projection as the oxygen atom at the highest numbered asymmetric carbon. So the configuration at the anomeric carbon is alpha, or as in alpha D glucose. D sugars, alpha is down, or the hydroxyl is down. Beta is up. L sugars, the reverse is true, and this, of course, relates to the customary Haworth drawings. So now we're going to take a break and work on drawing some of these structures together and talk a little bit more about them.